Imagine, just for a second, that you have a cheat code for the stock market.
Oh, I think everyone wishes they had one of those.
Right. But I don't mean like a crystal ball that magically tells you the future. I am talking about something much more grounded, but, arguably just as powerful.
Okay, I'm listening.
Imagine you have a way to perfectly calculate the exact, the so-called fair price of a really complex financial bet.
Down to the exact decimal.
Down to the decimal, and you have it long before anyone else on the trading floor even figures it out.
It is a fascinating premise. I mean, the entire history of quantitative finance is basically a search for that exact tool.
Yeah.
We all want a perfectly calibrated calculator that, removes the guesswork and turns the absolute chaos of human trading into predictable mathematical order.
And that desire for the perfect calculator, that's really the engine driving our deep dive today. We're exploring this brilliant 2024 paper.
Ah, yes, the paper by Daniel de Souza Santos and Tiago Alessandro Espinola Ferreira.
Exactly. It's titled Neural Network Learning of Black-Scholes Equation for Option Pricing.
Which is quite a mouthful. But what makes this specific paper stand out is how it bridges two completely different areas of finance.
It really does.
It takes this foundational problem that traders have wrestled with for, well, decades, and attacks it using incredibly modern, highly specific computational tools.
And that is exactly our mission for this deep dive. We are going to explore what happens when you take a 50-year-old Nobel Prize-winning mathematical formula.
A very formula that basically built Wall Street as we know it today.
Yeah, that exact one. What happens when you take that and supercharge it with modern artificial intelligence?
But to really appreciate how they fixed the math, or even to understand why they brought AI into the mix in the first place, we have to start with the actual financial instruments they're pricing.
Right, the options.
Exactly. The paper focuses entirely on derivatives, specifically options.
Okay, so let's unpack the bet itself. The paper looks at the two main flavors, right? Call options and put options. So a call option is essentially buying the right, but importantly, not the obligation, to purchase a stock at a guaranteed price later on.
That's the textbook definition, yeah.
I always think of it like paying $10 today to pre-order a highly anticipated video game, locking in a $60 purchase price.
That is actually a very grounded way to look at it.
Because if that game becomes incredibly rare and the street value shoots to $100, I still get to buy it for my locked-in $60. I make a massive profit.
Right. You exercise your right to buy.
But if the game comes out and it's just terrible and retailers discount it to $20...
You just walk away.
Exactly. I lose my $10 pre-order fee, sure, but I am not forced to buy a $20 game for $60.
The researchers illustrate this dynamic using a specific stock scenario. They ask you to imagine a company, let's call it company ABC, currently trading at a spot price of $35.57.
Okay, tracking so far.
In their example, you buy a call option with a strike price of $30 set to expire in 90 days.
So I now hold a contract guaranteeing I can buy ABC stock for $30 3 months from now.
Precisely.
And if the stock rockets up to $40, I exercise my option. I buy the stock at my guaranteed $30 strike price, turn around, and immediately sell it to the market for $40.
And you just pocketed a $10 profit per share.
But if the stock tanks to $20, the option, well, as the researchers put it, it turns to dust. It's just useless.
Yep. The person who sold you that option keeps your initial fee, and you take the loss. Then on the flip side of that, we have the put option.
Right, the put.
If a call option is a coupon for potential profit, a put option acts much more like an insurance policy.
Almost like buying gap insurance on a new car.
Basically, yeah. It gives you the right to sell an asset at a specific guaranteed price no matter how far the market falls.
The researchers give an example of company BCD trading at $38.51, right?
They do.
So if I decide to write, which just means I issue and sell a put option to someone with a $45 strike price, I am selling them an insurance policy.
You are guaranteeing that they can sell their stock for $45.
Which is incredibly risky for me, the writer of the option, if the market turns.
Oh, absolutely. Because if BCD stock plummets to $25, the person holding that put option is absolutely going to use it.
Yeah, why wouldn't they?
Right. And you are legally forced to buy their stock at that agreed-upon $45, even though it is only worth $25 on the open market. You absorb a massive loss.
Yikes. But if the stock goes up to $50, they aren't going to force me to buy it for less than they can get on the open market.
Exactly. The option expires worthless, and you just keep the premium they paid you for the insurance policy.
Now, there is a crucial distinction the paper highlights regarding when these options can actually be used.
Yes, the difference between American and European options.
Right. American options allow you to exercise your right to buy or sell at literally any point up until the expiration date.
Whereas European options, they can only be exercised on the exact date of expiration. And this paper exclusively studies European options.
I am assuming that's because the flexibility of an American option makes the math like way too complicated to easily model.
Precisely. Because an American option can be triggered at any second. Calculating its value requires mapping out almost infinite probabilities.
Well, that sounds like a headache.
It is. European options, having a fixed expiration date, provide a rigid structure that allows for much more elegant mathematical modeling. But this raises an important question.
How do you know what that coupon is actually worth today?
Exactly. If you have this European contract that is only good for one specific day 3 months from now, what is that piece of paper worth right now?
And answering that question takes us straight to the legendary math that built the modern derivatives market.
The Black-Scholes model, developed in the 1970s.
It's famous.
Oh, it was a revolutionary breakthrough. It actually won the Nobel Prize in economics.
Wow.
For the first time, traders had an analytical solution, a concrete mathematical formula to calculate the fair value of a European option.
But the paper defines the Black-Scholes model as a second-order parabolic partial differential equation.
It does, yes.
Okay, let's unpack this. Because to anyone who hasn't spent half their life in a university math department, second-order parabolic partial differential equation just sounds like a terrifying wall of jargon.
I mean, fair enough.
Can we get a plain English translation of what this math actually does?
Sure. At its core, a differential equation is just a way to map out how multiple moving parts interact and change over time.
Okay.
The Black-Scholes formula takes 5 moving parts: the current stock price, the strike price of your option, the time left until it expires, the risk-free interest rate of the broader economy, and the historical volatility of the stock.
And it just churns those 5 variables together to spit out a fair price.
Exactly. But the most surprising detail the researchers focus on is how you can mathematically disguise this equation.
Wait, I remember reading this part. Through a series of variable substitutions, the researchers showed that the Black-Scholes equation can be rewritten entirely as the heat transmission equation on a metal bar.
It is a stunning mathematical parallel.
It really is.
The way an option's price changes or diffuses over time mathematically mirrors exactly how heat dissipates through a solid object.
Wait, I'm losing the thread here slightly. How does a stock price turning into a temperature reading actually help us understand financial markets?
Think about lighting a match under one end of a long metal bar.
Okay, I'm picturing it.
The heat doesn't instantly teleport to the other side, right? It diffuses, spreading out predictably over time, depending on the properties of the metal.
Right.
Black-Scholes treats the underlying stock price, like that match, and time like the length of the metal bar. The value of the option diffuses and spreads out as it gets closer to expiration.
So what represents the type of metal in that analogy?
The volatility of the stock.
Oh, okay.
Just like copper conducts heat faster than iron, a highly volatile stock diffuses price changes faster than a stable one.
That makes so much sense.
To make this work mathematically, the researchers mapped the specific variables. They took the current stock price, designated as S, and time, designated as T, and transformed them into generalized variables, X and tau.
And by doing this mapping, the option's actual financial price gets transformed into a generalized heat value, represented by the letter U.
Yes. Solving for how heat moves through this theoretical metal bar gives you the exact same curve as how the options price moves through the market.
But here's my question. If we have this beautiful, elegant, Nobel Prize-winning math that perfectly equates stock options to the laws of thermodynamics, and we can solve it analytically on a chalkboard.
Why bring AI into it?
Exactly. Why are we bringing artificial intelligence into this? Isn't math just math? If the formula works, why fix it?
That is the exact challenge the researchers set out to address, and they answer it by pointing directly to the charts in their data.
The actual market data.
Right. The traditional analytical solution of Black-Scholes is beautiful in theory, but it relies on some very flawed assumptions about how reality works.
What kind of assumptions?
Well, it assumes a perfectly frictionless market with constant volatility, where trading happens continuously without any transaction costs.
But if you're listening to this and you have ever managed a 401k or watched a stock ticker during a panic, you know the market is anything but frictionless.
Not at all.
It is driven by human behavior, panic, greed, sudden liquidity freezes.
Exactly. When you apply the pure analytical formula to the messy reality of the real-world derivatives market, it struggles.
How bad does it struggle?
Well, for dates that are far away from the option's maturity date, the traditional formula practically just points to the current stock price.
It just gives up.
Essentially, it doesn't accurately capture the premium people are willing to pay for the time value of the option. It only converges to the true, real-world market price right at the very end of its lifespan.
Which means traders relying purely on the textbook formula are essentially flying blind for months until the final moments before expiration.
That gap between theory and reality is why the researchers decided to intervene.
Right.
Since the pure mathematical solution falls short, they turned to an artificial neural network to solve the differential equation numerically instead.
And here's where it gets really interesting.
Yeah.
They did not just throw a massive data set at ChatGPT and ask it to guess the stock market.
No, not at all.
They treated solving this specific math equation as an optimization problem. They built a highly specialized AI whose entire universe consists of this one differential equation.
The technical architecture they used is fascinating.
Hmm?
They built what is called an MLP, or a Multilayer Perceptron neural network,
And they constructed it using a Python 3 library named NeuroDiffic.
which is specifically tailored for solving differential equations, yes.
They outline the architecture as a 2-3-2-32-1 setup. Help me visualize what that means inside the computer.
Let's break it down layer by layer. The 2 represents the 2 inputs.
Oh.
The network is fed that modified price variable, the x, and the modified time interval, the tau. So it is receiving the starting heat and the time.
And those inputs go into the middle numbers, the 2 layers of 32 neurons.
Correct. 2 hidden layers, each containing 32 artificial neurons.
Got it.
Think of those 64 total neurons as specialized detectives. Each one is looking for a very specific nonlinear pattern in how the option's price reacts to the inputs.
So they weigh the data, communicate with each other, and finally condense all their findings down to the final one in that sequence.
The single output, the predicted price of the option.
That's amazing.
Yes. But to make those neurons learn effectively, they used specific mathematical functions. The paper mentions a hyperbolic tangent activation function.
Which basically determines how strongly a neuron fires when it spots a pattern, right?
Exactly. But more importantly, they use the atom optimization algorithm to train the network.
Okay, another piece of jargon. What is the atom algorithm actually doing?
Think of the atom algorithm like a highly advanced smart thermostat for the AI's learning process.
A smart thermostat.
Yeah. When an AI learns, it takes steps toward the right answer. If it takes steps that are too big, it overshoots the answer. If the steps are too small, it takes forever to learn.
Oh, I see.
The atom optimizer constantly adjusts the size of the AI's learning steps in real time, ensuring it zeroes in on the most accurate prediction without wasting computational power.
And they let the system run for 30,000 epochs, meaning it cycled through its learning process 30,000 times.
Yes, 30,000 iterations.
But the mechanism of how it learned is what really blew my mind. It isn't a traditional forecaster. It isn't just looking at past prices and making a statistical guess about tomorrow.
That is a crucial distinction.
Yeah.
The AI is programmed to minimize the residual error of the differential equation itself.
Which means what in practice?
It means the AI is essentially practicing the underlying Black-Scholes math over and over again, trying to solve it perfectly.
Yeah.
But here's the trick. It is constantly constrained and corrected by real-world boundary conditions. In this case, those boundary conditions are the actual historical payoff data from the real market.
So it is like taking a brilliant math student, giving them a textbook formula that is slightly outdated, and then continuously grading their homework against what actually happened on the trading floor that day.
That's a great analogy.
The AI realizes the textbook theory is slightly disconnected from reality, so it mathematically adjusts its own internal logic to bridge the gap.
That is a perfect way to conceptualize it.
Yeah.
But, a theoretical model, no matter how clever the neural network architecture is absolutely useless if it falls apart on a chaotic trading floor.
Oh, for sure.
To prove this actually worked, the researchers needed a high-volume, highly volatile testing ground.
And they didn't take this to the New York Stock Exchange. They tested it on the B3, which is the primary stock exchange of Brazil.
A very strategic choice. The Brazilian market provides a robust, incredibly active environment. To ensure the neural network had enough trading volume to learn effectively, they focused on data from two massive Brazilian blue-chip companies, Petrobras and Vale.
Just for context, Petrobras, trading under PTR4, and Vale, trading under VALE3, are absolute titans in the global energy and mining sectors.
Huge companies.
Their options contracts are heavily traded every single day.
The researchers narrowed their focus to specific series of options for these companies. They used the A series, which were options expiring in January of 2023, and the D series, which expired in April of 2023.
I found it interesting that they entirely excluded put options from their test. They only looked at calls.
Well, they were forced to by the data.
Really?
Yeah, in the specific timeframes they were analyzing on the Brazilian exchange, the trading volume for put options was simply too sparse.
I see.
If you feed a neural network low-volume data with huge gaps of time between actual trades, it cannot optimize its internal math. It needs a constant stream of information.
And call options provided the dense data points required. They also locked in some environmental constants to keep the math clean, right? In Brazil, options universally expire on the third Friday of the month.
Yep.
And for the risk-free interest rate variable, which is governed by the Selic rate down in Brazil, it remained at a constant 13.75% throughout the entire data period.
So the stage is completely set. We have our Black-Scholes heat equation. We have a specialized 32-neuron AI trained 30,000 times to solve it. And we have real-world, high-volume data from Petrobras and Vale to test it against the traditional analytical formula.
The ultimate showdown, machine versus math. Did this Python script actually manage to beat a formula that won a Nobel Prize?
What's fascinating here is the neural network absolutely dominated the traditional analytical solution.
Right.
It wasn't even close.
The visual charts they included in the paper are striking. They plot the actual real-world market price of the option as a blue line.
Right.
The traditional mathematical formula is a magenta line. And for months, that magenta line is completely divorced from reality, hovering way above the blue line.
Yeah, way off.
But the neural network's prediction, the green line, drops down and hugs the real-world blue line almost perfectly right from the very first day.
The AI didn't have to wait until the final days before expiration to calculate the actual value of the option. It recognized the true behavioral dynamics of the market immediately.
That's incredible.
The researchers also noticed that the AI performed exceptionally well under specific conditions. In the money options, or ITM options, produced the absolute lowest estimation errors.
Just to clarify, in the money means the strike price on your coupon is currently lower than the actual price of the stock, right? The option already has intrinsic value.
Exactly. Because an ITM option is already profitable, it naturally attracts a much higher trading volume.
Of course. Volume again.
And the golden rule of neural networks applies here. More high-quality data leads to tighter, more accurate predictions.
Let's contextualize some of these data drops because just throwing out numbers doesn't always capture how impressive this is. They use a metric called mean absolute error, or MAE, to measure how far off the predictions were from reality. The closer to zero, the better.
Yes.
For Petrobras, their most accurate prediction was on the PTE 266 series option. It had an MAE of just 0.670.
To put that in perspective, an MAE of 0.67 means that when pricing a highly complex derivatives contract, the AI was, on average, only missing the exact true market price by a fraction of a single Brazilian real.
That's wild.
It is an astonishing level of accuracy for an instrument driven by human trading.
And for the Vale stock, the best prediction was the Vale E765 series. That had a mean absolute error of 3.435 and a mean square error of 15.172.
But again, even at its worst, it drastically outperformed the traditional mathematical formula.
Oh, without a doubt.
The researchers provided a fantastic benchmark to prove just how far the technology has come. They compared their 2024 results against a similar study conducted in 2009 on the Hong Kong market.
I saw that.
That 2009 study was considered a massive success at the time, and its best neural network achieved a mean absolute error of 14.3.
And this new model, tested on Petrobras, achieved an average MAE of around 2.6.
It is roughly 7 times more accurate than previous benchmarks.
Wow.
I mean, that is just a massive leap forward, right? It represents a quantum leap in our ability to computationally bridge the gap between financial theory and the reality of the trading floor.
So what does this all mean? If you are a quantitative analyst on Wall Street, do you just throw away a 50-year-old foundational formula overnight because some researchers built a better Python script?
Well, if we connect this to the bigger picture, the takeaway is that we don't have to throw away our foundational economic models at all.
We don't.
No. The underlying architecture of the Black-Scholes equation is still incredibly sound. What this paper proves is that the flaw isn't the equation itself.
Right.
The flaw is trying to solve it analytically as if the market were a perfectly frictionless chalkboard.
Which we know it isn't.
Exactly. By using a neural network as a reality-constrained calculator, we can finally solve these classic theories in a way that respects the messy human reality of economics.
It is a phenomenal piece of research. To briefly recap the journey we just took, we started by looking at a simple call option, which is essentially a financial pre-order for a stock.
Yep.
We learned that the 1970s math used to price that contract is mathematically identical to calculating how heat diffuses through a solid metal bar.
The thermodynamics of finance.
Exactly. And finally, we saw how researchers used a 32-neuron artificial intelligence, guided by a smart thermostat algorithm, to optimize that math against real-world data from the Brazilian stock exchange.
Predicting the fair price from day one with unprecedented accuracy.
It forces us to reconsider how we apply theoretical mathematics to live markets.
It really does.
And it leaves me with one final, slightly provocative thought for you to mull over. If two researchers can build a neural network that practically perfectly predicts the fair price of a financial bet from day one, what happens to the global stock market when every single trader, bank, and hedge fund has this exact AI running on their desk?
That is the million-dollar question.
If everyone holds the exact same perfectly calibrated cheat code, does the advantage simply disappear into the noise, or does it fundamentally and permanently change what the concept of risk even means in modern finance?
It's a completely new paradigm.
Something to think about next time you check your portfolio. Thank you so much for joining us on this deep dive. We will catch you on the next one.